Hello guys, and welcome to my YouTube channel. In this video, I'm going to be interpreting a hydrogen NMR or a proton NMR. Let's get into it. But first, please make sure to leave a like, comment, save, and or subscribe to my channel if you like my content and you find it helpful. That would mean a lot. Step 1 of every single proton NMR question is if you're given the molecular formula, which you most likely will be in a second year course especially, is to determine the DBE, which is the double bond equivalence. The formula for this, well, one of the variations is 1/2, and then 2 times C4, which is the number of atoms that make 4 bonds. So for example, carbons, plus the number of atoms that make 3 bonds, so nitrogens, minus the number of 1 bonders, so 1 bonders would be hydrogens and halogens, and then halogens, and then plus 2, which is kind of just a buffer. Hopefully you wrote that down. So if we had to do this for the molecular formula we were given, it would be 1/2 times 2 times how many carbons? Well, there's 6 carbons, so 2 times 6. And then plus how many nitrogens? There's no nitrogens, so 0. Minus the number of 1 bonders, so there's no halogens, there's only hydrogens, and there's 10 of them. So minus 10. And then plus 2. If I plug this into a calculator, I should get 1/2, or if I just did this in my brain, 1/2 of 12 minus 10 plus 2, or 1/2 of 4, which is going to be 2. So the double bond equivalence is equal to 2. So this is equal to 2. So what does that mean? It means that this structure has 2 double bonds. 2. And I'm going to keep this in my mind for when I do the final part of this interpretation and I put all the data together to determine the structure. So next, I'm going to go through each of the peaks and perform IMP. If you don't know what IMP means, go to my last video. But it means integration, multiplicity, and ppm. Starting with the integrations. In short, if you have an integration that is equal to 1, you're assuming this is a CH group. If you have an integration that's equal to 2, well, this would be a CH2 group. If you have an integration equal to 3, well, hopefully you see the trend here. This would be a CH3 group. What if I had an integration equal to 4? Well, what is 2 times 2? Well, 2 times 2 is equal to 4. So this would mean you potentially have 2 CH2 groups. But these 2 CH2 groups would be symmetrical, so the same CH2 group. If you have an integration is equal to 6, well, you most likely have 2 CH3 groups. Okay, let's try this. An integration equal to 9. Well, this would be 3 CH3 groups, so on and so forth. And this is kind of just a rule of thumb. Going back to our question, an integration of 4, well, I either have 4 CH groups or I have 2 CH2 groups, which is way more likely. So for now, I'm going to say I think this is 2 CH2 groups. If I'm wrong, I would go back and revise. But it's probably going to be 2 CH2 groups. And then multiplicity, I need to count the peaks. 1, 2, 3, 4. So 4 is equal to a quartet. And quartet is equal to 4. But what the multiplicity really tells me is how many neighbors there are. So what I want to do for the neighbors is equal to multiplicity minus 1, where multiplicity is going to be 4 minus 1. So the neighbors is equal to 3. So what does this mean? Well, I have 3 neighbors. If a CH2 group has 3 neighbors, this means it is bonded to a CH3 group. So it has a neighbor that is a CH3 group. And then the ppm tells us if this group is attached to something electronegative. if it is in the electron poor region of the spectra, so more left. This group is around 4.5, so that is very electron poor. So what this tells me is it's potentially attached to something delta minus. So a CH2 is attached to something delta minus. So I'm going to do this same analysis for the blue peak. So integration equal to 6, that means I have a CH3 group or 2 of them that are equivalent. My multiplicity is equal to 1, 2, 3. So a triplet. So that means how many neighbors do I have? Neighbors is going to be 3 minus 1 is equal to 2. So what does 2 stand for? 2 stands for CH2. Say it with me. 1 stands for CH. 2 stands for CH2. 3 stands for CH3. So this CH3 group is attached to a CH2 group. Who is that CH2? Well, it's this CH2. You should always be able to find that partner that you've identified. So this would be pretty much 9 out of the 12 marks that you need to come up with to complete this question. So if you've done this, then you've pretty much gotten all the marks already. Oh, but wait, I actually need the ppm. The ppm, this is at around 1.5, so this would be E minus rich. So I'm going to assume the CH3 is, well, it's bonded to the CH2 group, so it's not going to be attached to something delta minus, therefore it's going to be electron rich, hence it's very right on the spectrum. Going to a new page, I'm going to take all the information that I have. So my molecular formula, my DBE, and then what I obtained from the spectra, which was that IMP told me I have 2 CH2 groups that are attached to CH3 groups, and this one is the same as this one. And what I mean by the same is there must be a plane of symmetry. So if you consider propane, if I split propane right in half, well, this CH3 group would be the exact same as this CH3 group. So the integration of these green hydrogens would be 6 because they're the exact same hydrogen. So whenever you have a DBE and you have oxygens, I'm going to assume there's either a carboxylic acid or I'm going to assume there's ester groups, OR. Since there's a DBE of 2, well, that means I either have 2 carboxylic acid groups because the DBE of a carboxylic acid group would be 1. So to have a total DBE of 2, I would need 2 of these groups. Same goes for the ester. So now the question is, do I put this on a carboxylic acid or an ester? What did we learn, better yet, about the CH2 group? We learned that it's E minus poor. So who would it be attached to? It's probably this R group. So I'm going to veto the carboxylic acid. I'm going to say, working with 1/2 of the structure, I probably have an ester group where this pink CH2 group is attached to the CH3 group, and it's electron poor, E minus poor, because it's a part of the ester group, where it's on the side of the oxygen, making it electron poor. So once you know for sure a component of the structure, what you're going to do is you're going to take the molecular formula, and I'm going to subtract off what I know. So I know right now that I have 1 carbon, 2 carbon, 3 carbon, so minus C3, and then minus H1, 2, 3, 4, 5. I know for sure I'm minusing H5, and then how many oxygens? O1, O2, O2. So what do I get left over? I get C3H5O2. Is this not the same molecular formula as this? Yes. And is there not an element of symmetry in my overall structure? Yes, there has to be. So does that not mean that I just have another one of these? Ah, yes. So now I have everything I need to make my final structure. So now the final question is, well, how do I put this together? Ask, who needs more bonds? Well, the CH2 group, they have 4 bonds. Every carbon likes to make 4 bonds. And this carbon has 1, 2, 3, 4 bonds. So it's happy. Nothing can be added to it. What about this carbon? Well, it's also attached to 1, 2, 3 hydrogens. Therefore, it doesn't want to make any more bonds. What about this oxygen? Can it make another bond? No. What about this carbon? Yes, this carbon right now only has 1, 2, 3 bonds. So that means it needs to make a bond to this carbon that also needs 1 more bond. And this would be your structure. Obviously, we shouldn't draw it like this, so we need to make it look a little bit nicer. So how this would look is you'd have one connected to the other one, and then your O, and then your CH2 groups, CH2, and then your CH3 groups, CH3 groups. Where if you chop this in half, you have that element of symmetry, where these CH2s are the same as these CH2s, and these blue CH3s are the same as these blue CH3s, accounting for the integration equal to 6, and the integration of the pink hydrogens would be 4. Okay, let's draw the spectra for this compound and see what we get to prove to ourselves that we did this right. So let's focus in on this CH2 group. So due to the element of symmetry, this CH2 group is equal to that CH2. So if I want to make a peak for it, the integration is going to be equal to 4, a total of all the hydrogens that are equal to one another. So what about its multiplicity? Well, its multiplicity is going to be the neighbors, n plus 1. So how many neighbors does it have? 1, 2, 3. So choose one of these hydrogens and then count 3 bonds away. 1 bond, 2 bond, 3 bond, gotcha. 1 bond, 2 bond, 3 bond, gotcha. 1 bond, 2 bond, 3 bond, gotcha. So the neighbors is equal to 3. Equal to 3 plus 1. So total, this is going to be 4, where we get a quartet. So we should have a quartet. 1, 2, 3, 4. With an integration equal to 4. That's quite electron poor because, oh, it's attached to an oxygen group. What about the blue hydrogens? Getting rid of the green. Integration for all the blue hydrogens would be 1, 2, 3, 4, 5, 6. Equal to 6. And now what's the multiplicity, which is n plus 1? How many neighbors does it have? Choose any one of the hydrogens and count 1, 2, 3 bonds away. Gotcha. 1, 2, 3 bonds away. Gotcha. So 2 neighbors is equal to 2 plus 1, which is the buffer. So multiplicity is equal to 3. So I should have a triplet, 1, 2, 3, in an electron-rich area, because it's a CH3 attached to a CH2. A CH2 group is not pulling away electrons. Hence, it's going to be electron-rich. Integration is equal to 6. And this would be the spectra that we were given in the beginning. So I've just convinced myself that I did this correctly. Hopefully this video was helpful. I hope you learned something. I went a bit more fast in this video, I would say. I skipped some components, and if you go back and watch my first video or the first videos that I made about HNMR, then you should be able to pick up on what I'm talking about when I talk about J3 and how to figure out a neighbor and how to figure out if something is electron rich or electron poor, and I also go a little bit more into the imp. Yeah. Please make sure to leave a like, comment, or subscribe to my channel if you made it this far. I hope this video was helpful. You guys got this. Keep on chugging along. And have a great night. Bye.